My name's Adam, and I'm a data scientist at Dataiku. And today I'm going to be speaking about an application for real-time machine learning, in particular about a project that we worked on to predict taxi fares in New York City using Dataiku's Data Science Studio. So for those of you that haven't heard of Dataiku or Data Science Studio, it's an awesome piece of software for end-to-end data science projects, from ingesting data through to machine learning, and then deploying those models into production. And that's what was used for the entire use case that you're going to see today. So to provide some context on the use case, we're going to start with some data, as all good data science projects should, which I imagine will confirm some of your intuitions about what's been going on over the last few years in the New York taxi market. So what you're seeing is the number of daily trips. Oh, signal's gone. Yeah. Okay, sorry about that, everyone. I guess we're going to have to go through the use case a little bit quicker now. But to try and pick up where I left off, we're looking at the trends in the taxi market in New York, and what we're seeing is that the traditional yellow cabs have been decreasing in the number of trips that are taken over the last few years, particularly since around 2015, when Uber really started to accelerate its growth in New York. And when we came across this data, this got us wondering what it is that makes Uber so much more popular than the traditional New York taxis, because after all, in New York there's normally so many yellow cabs around that it's often easier to just hail a cab from the street than it is to get out your phone and order an Uber. And one obvious reason for that would be the price. But as we all know, with Uber's mysterious dynamic pricing algorithm, we suspected that actually some of the time the traditional cabs might be cheaper. And after a little bit of research, we found out that indeed, when the traffic is slow moving and Uber's surge pricing is high, that the traditional taxis can be cheaper. So we wondered whether if you had the fare for a traditional yellow taxi cab up front, so you could compare the price with Uber or Lyft, whether that would then encourage more people to take trips with a traditional taxi. And in fact, the New York City Taxi and Limousine Commission, who are the company behind the traditional yellow cabs, are aware of the trend that the traditional taxis are seeing declining business. And in fact, last year, they actually published some of their historical data on the well-known website Kaggle to ask the data science community for some help with predicting their fares and seeing if they could help them become more data-driven to keep up with the competition. And so we decided to take up that challenge to predict traditional taxi fares. And so for the rest of my talk today, I'm going to walk you through that end-to-end journey from discovering the initial data through the feature engineering, the machine learning, and then the deployment of the model into a real-time application. So the journey began, as most do, with discovering the data that we had. And it turned out that the raw data was actually fairly straightforward. So we had 5 years of history and just 4 features. So we had the date time of the trip, we had the number of passengers, the latitude and longitude of the pickup, and the latitude and longitude of the drop-off. So we started exploring that data, taking a look into some of the distributions, and we have found some interesting things. So we saw that there were some trips that had the same pickup and drop-off location, so were clearly round trips that were lasting over 5 hours and costing over $800. So I'm guessing it's business people going to a meeting, making the taxi wait outside for them, keeping the meter running, and then coming back. But in fact, we found out that they could have got a private limo with a driver for less money than using a traditional taxi and keeping the meter running. But I guess that's just New York. We also found that trips to the airport generally had a flat rate. And so that meant that they were often cheaper than similar distance trips within Manhattan. And also we found some things that were down to just plain dirty data. So there were some rides that seemed to be costing over $94,000, which seems a little extreme even for New York, as well as some rides that were a few hundred kilometers long, and even rides that ended up in the bottom of the Hudson River. So I certainly hope that was bad data anyway. So once we'd got a good feeling for our data, we then needed to move on to some feature engineering. And we realized that given that we had just 4 features, we were going to have to do some pretty creative feature engineering to be able to get a good predictor of the fare price. So we started off just diving straight in, creating any features that we could think of. So we started with simple geometrical features, so the L2 shortest distance between 2 points. We also created the L1 distance, as we thought that might be interesting given New York's grid-like structure. Even have assigned distances between lat longs to get actual distances in kilometers. Direction of the trip, north, south, east, west. And then time-based features as well. So we extracted the hour of the day of the week, and also some longer-term time features, such as the month of the year, to try and look into seasonality a little bit. But we realized that in order to extract the signal from the noise, we were going to need to aggregate the data in some way, and particularly because we knew that traffic was going to be a key feature in the fare price, that we were going to have to combine the route somehow with the time of day to get that. And so what we did next was to apply a simple clustering algorithm. We used scikit-learn's mini-batch k-means to cluster our data on both the pickup location and the drop-off location into 50 different clusters. And that's what you can see on the left of the screen there. And in fact, those clusters that we formed matched up fairly well with New York City neighborhoods. And what this then allowed us to do was to group trips into the cluster that they were going from and the cluster that they were going to, so we could then aggregate our data. And with that, we were then able to start getting to some really interesting features. So we started using window functions to look at, say, for example, the past 10 trips from one cluster to another, and then we could take the average fare for those previous trips. Similarly, we could look at the trips from one cluster to another at a particular hour of the day or day of the week, and get the average fare for the previous trips for there. And that then gave us a proxy for the amount of traffic on particular routes at particular times. And I thought that was pretty cool, that we were actually able to get a proxy for the level of traffic without using an external data source, just by creating some interesting features from our data. But at this point, we'd already ended up with hundreds of features, and we knew that if we carried on with those, we were going to end up with problems with overfitting. So we needed to kind of go back to the root cause of the problem and to reduce down our features. And in fact, it was only at this point that we found that the business rules on which the New York City taxi meters are based were publicly available online. And that's what you can see there. So we realized that actually we'd managed to capture a lot of those rules intuitively through the features that we'd created, but we could refine some of those a little bit. So rather than just taking the hour of the day, we could take a explicit flag that said whether or not that was a peak hour or not a peak hour. But also we realized that we weren't capturing everything. And so it was at this point that we turned to an external data source. We actually used the Here API to get route level information. But obviously external APIs can be expensive and we didn't want to overload it with requests. So what we did was, rather than applying taking an API request to get external data for every single trip, we went down to the cluster pickup and cluster drop-off for each hour of the day, for each day of the week. So that significantly reduced the number of API calls we had to make, but still gave us granular enough information on the routes. So we could get the drive times, including traffic. We could get flags for whether the route included a motorway or a toll road or a toll bridge and those kind of things. And with that additional data, we then had managed to capture most of what was in the business rules for the fare meter. And we then applied some feature reduction, so some automatic feature reduction just based on correlation with the target, and also some manual feature reduction based on some initial models. We looked at what variables were most important, and then we could then reduce that down to around 100 features, which seemed optimal for our initial models. So once we'd decided on a set of features, it was then time to train the full model. And previously, for our initial models, we'd been using simple out-of-the-box scikit-learn models. But when we tried to scale that up, we found that we were only able to use about 30% of our training data on our machine before we started running out of memory. And so we started to then look at other options and other algorithms we could use, and came across Microsoft's Light GBM algorithm. So Microsoft's Light GBM algorithm helped us with our out-of-memory issues for a few reasons, but one of which is because it automatically bins features, numerical features, which reduces the memory required to store those. And we found that with Light GBM, we were actually able to train a model that used just over 50% of our training data within our memory requirements. And not only that, but it was also faster to train, and we were able to get a better accuracy. So the problem with the Light GBM model was that we were still seeing significant overfitting, both at the feature level and on a row-by-row level. So we started playing around with the hyperparameters, and specifically we found that because we had so many features, one way that we could improve the accuracy on our test set was to reduce the number of features that were contained within each tree in the model. So we reduced the column samples in each tree to 60%. And this helped us reduce the overfitting. Similarly, because we had so much training data, we needed to reduce the overfitting on a row-by-row basis. And we didn't want to limit the depth of the trees, since Light GBM trains on a leaf basis. So it's a leaf-based growth rather than a level-based growth. But instead, what we found helped more was to increase a minimum on the gain that our model had to get to cause a split in one of the branches. So we increased the minimum gain to cause a split from 0 to 0.25, and this helped us find the optimum performance on our test set. And you can see some of the final parameters we ended up choosing in that code sample on the right there. So once we'd set our hyperparameters and trained the full model, we found that it took around 12 hours to train, and we were able to achieve an RMSE accuracy of $2.9. So for our individual fare estimates, we were about plus or minus $1.4. And this was firstly in the top 10% of the Kaggle leaderboard, which we were pretty happy with. But also we thought that would be sufficient for somebody who's about to make a taxi trip to decide whether or not that price was reasonable for where they wanted to go. So at this point, our workflow looked something like what you can see on the screen there. So we're taking our initial train and test data and stacking it together so that we can apply the same pre-processing to both. We're then applying our clustering algorithm to each of those trips to see which cluster it's going from and to. From there, we're then applying our window functions on that top branch to get the average over the last few trips, and also grouping down to cluster by cluster routes, for which we then call the Here API to get the external traffic data on that bottom branch, before joining all of those features together, separating our test data back out, training our model in green on the bottom there, and then applying that model back to our test data and cleaning up the results ready to submit to Kaggle. So that was an overview of the workflow. And for Kaggle competitions and a lot of academic data science problems, that's the end of the product and the workflow. But for real life data science, you need to deploy that model somewhere and productionalize it for it to be useful and valuable. And so what we wanted to do was then to take that model and to deploy it as part of a proof of concept application to expose the fair to our users. And so that's what we decided to do. So luckily, turning a model into an API endpoint on Data Science Studio requires just a few clicks. So we were able to do that fairly straightforwardly. And on the screen there was actually supposed to be a little animation of how simple that is to do. But feel free to ask about that later, and I can talk you through how that works. But in fact, we needed not only to deploy our model to an endpoint, but also we needed to do the feature engineering in real time as well. So the way we did that was to create an API service structure, which is detailed on the screen. So we had a Python endpoint which acted as a wrapper. So that took in our raw features and then called another endpoint which would apply our clustering algorithms to those latitudes and longitudes to get the clusters. And then once we had the clusters, we could then call another endpoint, the Here API, to enrich with the traffic level data. And then finally, we could pass all of those parameters to our model endpoint to get back our prediction of the fair. So that was the API service that we created. But one thing you might have noticed is that the window features are now missing from that API service. And the reason for that was that we realized that on going to real time, unlike in our training data, we'd no longer have a continuous feed of trips and the fare prices. So it wouldn't be possible to get an average of the fares over the last 10 trips. So we were forced to remove those window features from our model. But luckily, since we now had the traffic data from the external API, this was a small loss in accuracy. And actually, even if we had been able to create those window features, it might have been worth losing that accuracy for the reduction in latency, since they can be quite computationally intensive to calculate. And then once we had that API service, we could throw a little bit of data scientist HTML and JavaScript on the top to make a rough and ready application to expose that model to our users. And that's what we did. So at this point, you're probably wondering whether it worked, and the answer is yes, and I was hoping to be able to know that. But given the issues that we were having, I'm not sure if I'm going to be able to get that up right now. It seems like I might not be able to get that to show now, which is a shame. But in fact, if you want to try it out, you can actually go to that URL yourself to give it a go. Or if you want to swing by the Dataiku booth sometime later on today, I can show it to you. But I'm sorry, I can't show it now. I'd hope to do it on my own laptop to show. But the app looks something like that. You could put in a pickup location. You could put in a drop-off location as well. set the time you wanted to travel. We're using the Google Maps API to pull through the map and set the route, and then you could hit get fare and it would come up with a price prediction based on our model. So that pretty much wraps up the use case, but just before I conclude, I just wanted to run through some of the things that we learned along the way as part of this data science project. So the first one, which I'm sure you've all heard a million times before, was to make sure that you understand the problem before building models. Now, I think we did a fairly good job of exploring the data for this particular project, but what we didn't realize was that the business rules on which the fares were based were actually available online until halfway through, and that would have definitely helped us with creating our features and realizing what was going to be relevant or not. And that actually links to the second one on creating features. So the lesson we learned was not just to keep creating features for the sake of it, because if you add too many features, you're just going to give yourselves headaches with overfitting later down the line. You need features that are relevant and, most importantly, causal for your target variable that you're trying to predict. But on the other hand, in terms of algorithms with relatively cheap computational power, you're free to try as many algorithms as you wish and to see what works best for your particular use case. And I'm sure many of you have heard of the no free lunch theorem that states that no one algorithm is going to be best across the board. But if you are interested in the Microsoft Light GBM algorithm and are having issues with storing your data set in memory, then I definitely suggest checking it out and seeing if it works for your use case. And finally, the last one was around simplifying the pipeline before deployment, whether that be batch or real time. But specifically for real time, it's worth simplifying the pipeline and asking yourself whether the features that you need to create in real time, whether the additional accuracy that you're getting from them are worth the cost in terms of the latency that you might be creating in getting your predictions back. So as for the window features in this example, that even if we had been able to compute them based on a real-time feed, it might not have been worth the increase in time that it takes for the model to return them. And finally, if you're interested in learning more about Dataiku's Data Science Studio, to bring your team together to work on data science projects like this one, then feel free to come by the Dataiku booth, which is just over there, to ask me or another member of the team about how DSS works and how it could help you with your use case. Or alternatively, you can try out a free version of the software by going on the website and downloading the community edition. So thanks very much for your time. I'm sorry about the technical issues and the hold-up. And as I said, if you want to see the demo, you're free to try the URL or to come over later. And for the few minutes that are left, I think, happy to take any questions from anybody now as well.